Hi. So this video covers the heat transfer process of conduction. In conduction, we've got heat transferred through a material. Say we've got just like a bar of material here, something like this. Maybe a coffee mug's not the best example, but you can picture just a solid hunk of metal. And let's say we have this one end of the metal over the top of a flame. Well, the atoms that are directly exposed to the flame there are going to start vibrating violently back and forth. So they're really going to be bouncing back and forth. Those atoms are going to slam into their nearest neighbors, or at least we can picture it as being like that. They're going to slam into their nearest neighbors. They're going to set their nearest neighbors vibrating back and forth. And then they're going to slam into their nearest neighbors, and they're going to vibrate back and forth. And it's this process of collisions of atoms through a material that is the process of conduction. This is different than the process of convection that I talked about in the last video. In conduction, our atoms are pretty much staying in one location, although they are vibrating back and forth. They're kind of stuck at that, around some specific spot in the material. So it's that they're colliding with their neighbors that's causing heat to transfer through the material. In convection, we've got fluids going in bulk motion. So maybe if it's air that is our fluid, the air is rising, the air molecules are rising from here all the way up to there, and so on and so forth. So conduction, it's just the heat that's being transferred because of collisions. In convection, I guess the molecules carry the heat with them as they move around. Okay. All right, so anyway, this is the process of conduction, and we have to have a material that this transfer process is occurring in. Typically, we think of this as happening in solids, but it definitely also happens in fluids. That would be liquids and gases as well. If we've got an object that transfers heat really well, then we call this a thermal conductor. If it transfers heat poorly, then it's a thermal insulator. Okay. All right, so we can quantify this with the equation that you see on the screen there. The symbol Q is the variable that we're using for heat. Remember, heat is just energy. We could call this capital E for energy, but we give it a special letter, I guess. So we're using capital Q. So the energy transfer that we see happening through this rod that's on the bottom of the screen is equal to the rod's thermal conductivity K. That's a function of the material. So different materials have different thermal conductivities. So Q is equal to K times cross-sectional area A. We can imagine that the thicker the pipe is, the more heat can be transferred through it, or the thicker the rod is, I should say, not pipe. I'm thinking about water, and it's really similar, honestly. But the bigger around our material is, the more heat can be transferred through it. So Q is equal to Ka, and then delta T. That delta T is the temperature difference between the two ends of our material. And then the next thing we have is small t. That's just time. And then we're dividing this all by the length of this rod, capital L. So that could be length, or that could be thickness. So if we've got a long rod, I don't know, a bar, we might think of that as a length. But honestly, something that we're concerned about a lot of times is heat transfer through walls. And in that case, it wouldn't really make any sense to talk about the length of a wall. Really, that would be thickness instead. So this L is thickness or length. Okay. All right. This basically just says exactly what I just said. So you can pause this and read it if you want to, but it's what I just said in words, written out for you to see. Here's a table of thermal conductivities for a couple different materials. We notice that metals have a lot higher thermal conductivity than gases. Makes sense. If we go down to the bottom, we can see some other materials. Those are, let's see, if you look down towards near the bottom, you can see wood. let's see here. Wood right there. So wood has a thermal conductivity of 0.15, which obviously is a lot lower than these metals, but is much higher than these gases. Interestingly here, although I wrote over it, so maybe I can erase that real quick. There we go. If we look at the thermal conductivity of water, it's 0.6, and it turns out that water is actually a better thermal conductor than wood is. And again, this is not bulk motion of the water. These are the water molecules vibrating back and forth, slamming into their nearest neighbors, and heat is transferred on down the line. All right, so let's see here. I think I've got a question for you next. It says, we're imagining a couple of different materials, a bar of aluminum, a bar of copper, and a bar of wood. A bar of wood, a piece of wood, whatever. And all of these are at room temperature. You pick up each one of these in your hand. Which one of these would feel coolest if you held it in your hand? And we're given the thermal conductivities of the materials, 240 for aluminum, 390 for copper, and 0.15 for wood. So they're all at room temperature. Which would feel the coolest if held in your hand? Just a reminder, your hand is not at room temperature. It's somewhere between room temperature and your internal body temperature, right? So it's going to be hotter than the material you're picking up. So pause the video, think about it, and get a response. Okay. So it turns out that it is copper. It's the one that has the highest thermal conductivity. So copper is the best at transferring heat. That means that if you've got a material, a piece of copper in your hand, it's going to be the most efficient thing of our three choices at transferring heat from a higher temperature object, your hand, to itself at a lower temperature. Okay. So copper is the answer here. If you just have a little bit of difficulty with this, we can imagine now that instead of having these three different materials at room temperature, we've stuck them out in the snow. So, and maybe it's a really cold day out, maybe it's 10 degrees Fahrenheit outside, a couple degrees Celsius, whatever. And then you go out there with your bare hands and you pick up the piece of wood, and you pick up the copper. Which one are you going to want to let go of quickest? Well, you know it's the copper. The copper is going to really feel cold to your hand, and that's because copper is a better conductor of heat. It basically transfers the heat out of your hand more quickly than the wood would. Wood. All right. So one of the things that we can use materials for is not only as thermal conductors, but also as thermal insulators. So if you think about the pink insulation that you might have in your attic, that pink insulation is not a solid material. Actually, it's got a bunch of air inside of it. And while there are small convective currents inside of those air pockets, they're very small. And air is a very good thermal insulator. So if we go back to that list there, so the convection really doesn't have much of an effect at all. We go back to this list and we take a look at air. Let's see, where's my air? Air is right there. It's 0.0256, really tiny in comparison to maybe some other materials that we might use, like, well, let's see, asbestos. Probably not a good idea to use asbestos, but it is an insulator that was used. All right. So those air pockets really increase the thermal insulation of our object, of our insulator. Let's see here. Yes. So the next thing I want to do is another problem for you. It says we're comparing concrete to air. And it says, what thickness of concrete? So how thick would I have to make a slab of concrete in order that it will conduct the exact same amount of heat, that it conduct heat at the same rate as a quarter meter of air? A quarter meter, how long is that? It's about that long, a quarter meter. So how thick would I need to make the concrete to be equivalent to have a thermal conductivity rate that's equivalent to a quarter meter of air. We're given the thermal conductivity of concrete. We're given the thermal conductivity of air. So pause the video and see if you can work this out. Okay, so it turns out it's 11 meters or approximately 11 meters. Now, how did we arrive at that? Okay. Well, here's how. We've got our thermal conductivity equation. This is Ka delta T over L, and this is specifically, I don't know why I chose to put that. Oh, there we go. That's why. It's a little glitch in my my screen. There we go. So we're asked about the rate at which these two different materials conduct heat. A rate is an amount over time. Specifically, if we look at the rate of heat conduction, that's the amount of heat per unit time. And so if I divide both sides of this Q equation by time, I end up getting that Q over T is equal to Ka delta T over L. Now, Q over T, there's something else we could call that besides just Q over T. Remember that Q is heat and heat is energy. So effectively what we have there is energy over time. And you might recall that energy over time is actually power. So power is energy over time. Whoops, that's good. Okay, power is energy over time. Or power would be equal to, then, if heat is energy, Q over time. All right. So let's then replace this Q over time with what it is. It's actually power. Okay. And this problem basically says that we want the power conducted through the concrete to be the same thing as the power conducted through the air. Okay, so we're going to hold on to that idea and create a little space here to work in. Go. All right. And I can go ahead and erase this as well. Okay. All right, so we want those two powers to be equal to each other. So we're going to have on the left-hand side K of concrete times area of concrete times delta T for the concrete divided by the length, thickness of the concrete is equal to all of the same quantities for air. Now, one of the things that you notice about the problem is that, well, we've got a lot of different variables there. So we're left with kind of a conundrum of, can we actually do this problem or not? Because we don't have all that information. But one of the things that we notice is that it says that the problem statement says all the other conditions are the same. That means that, I've got the same temperature difference across the concrete as I do across the air. Otherwise, it wouldn't make sense to ask this question. Same thing with the area of the material. I've got the same, the same cross-sectional area for the material, whether it's concrete or air. So those items are going to cancel out. As a result, I'm going to be left with, let's see here, K concrete over L concrete is equal to K air over L air. I can now cross multiply L air, K concrete equals K air L concrete. And now I want to solve for the thickness of the concrete. So I divide both sides by the thermal conductivity of air. And I will end up with L concrete is equal to LA KC over KA. So erase that real quick. There we go. Pen. Air. There we go. Okay. So if I fill this in now, 0.25 meters times my thermal conductivity of concrete, which is 1.1, divided by my thermal conductivity of air, which is 0.0256. Notice there that the constants, or excuse me, the units on my my thermal conductivities will cancel out. So I don't really need to write those down when I plug in the numbers. And this should give me the result that is circled on the next slide, which is about 1.1 meters. All right. I'm going to break the video now, and I will come back with something else in the next one.